This video will be about patterns and functions. A function is a relationship that assigns exactly one output value for each input value. You can apply functions to a lot of situations. So some real-life situations where you could write a function, for example, is height versus a person's shoe size. If someone is a certain height, they would have approximately this shoe size. Or you could say the cost versus the number of people going to a movie. If a movie ticket costs $10 for one person, it's $10, so your input is one person, output is $10. For two people, so input of two people, then you would have an output of $20, because then you have to pay $20 to get both people in. So there's a couple of examples of functions, of real-world functions you could make. So a function rule is a mathematical expression that describes the function relationship. So we talked about the movie. We had $10 per person. So let's say it cost $10 per person to go to a movie. So that's the amount you're changing by for every person. If you had 3 people, $30, 4 people, $40. And when we write these function rules, we also need a starting amount. So that's the amount we're changing by. And then we need a starting amount. So when we do our starting amount, our input is always 0. So if we had 0 people, it would cost us $0. So 0 people, we have an output of $0. So we can write a rule for this. So the common rule you're going to be using in this section, sometimes it's called a linear rule or a line, but the common rule is to have your output variable, so it goes output, which we usually put as y, equals your starting amount, which we're going to call b, plus your amount of change, so I'm going to call amount of change x, times your input variable. Now later on in math, they will write this y equals mx plus b instead of y equals b plus mx. But for this section, they write it this way, so I'm showing it this way. Also, we're only going to be putting in actual number values for the b and the m. We will leave the variables. You could change the variables to match the situation. I could say my output is the cost and my input is the number of people. So I could put c and p instead of y and x. Doesn't matter which variables we use, as long as we stick to this common rule that we're going to be using. So we said our starting amount is $0. For 0 people, we had an output of $0. And the amount of change is how much we're paying per ticket, so $10. I don't need the dollar symbol though, so I'm just going to write 10x. Or if you'd rather use the cost equals 0 plus 10 times the number of people, then you know exactly what the C and P are standing for, cost, number of people. Second, if you can simplify, we should, 0 plus anything is just that other term. So 0 plus 10p is just 10p. Now we could use that to find the cost for any number of people. If I wanted to know how much it was going to cost for 70 people to go to a movie, I would just replace the number of people with 70. 10 times 70 is 700. So the purpose of this rule that we're writing is so that for higher numbers, we don't have to add up every single one together. We can figure out this cost or whatever the situation may be by just plugging in our input value. So these function rules are used to make it simpler, especially as your values get larger and larger. So let's look at another example. Let's say we're building houses out of toothpicks. So let me show you an example of what one house would look like. We're building one house out of toothpicks. Each line represents one toothpick, and we're going to do just the classic child style looking house. So this house is made up of 1, 2, 3, 4, 5, 6 toothpicks. So if we did 2 houses, 1, 2, 3, 4, 5, 6. Now these houses are going to be connected together. 7, 8, 9, 10, 11 toothpicks. And then let's do one more, 3 houses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 toothpicks. So we often take this information and data we find and write it as a table. So we can have the number of houses compared to the number of toothpicks. 1 house, 2 house, 3 houses, 6 toothpicks, 11 toothpicks, 16 toothpicks. So looking at this, we need to fill in that equation again. So again, we had this y equals b plus mx, where we really just need to find the starting amount and the amount of change. So the amount of change is pretty easy. We're looking at the amount of change in the output. So our input is how many houses, our output is the number of toothpicks. So to get from 6 to 11, that's 5 more toothpicks. And to get from 11 to 16, that's also 5 more toothpicks. If they were different, we couldn't use this common function rule. But all of these should be following this common function rule for this section. So it should match every time. So we're adding 5 every time. That's the amount of change. That means m is 5. If we want to, again, use variables that relate to our situation, our input was houses, so instead of x, we'd use h. Our output was toothpicks, so instead of y, we'd use t. So now we need our starting amount. Now we know our starting amount should be for 0 houses. So we actually have to go backwards. So going to the right is considered going forwards. We're adding 5. If we're going backwards, we need to go the opposite operation as well. Instead of adding 5, minusing 5. 6 minus 5 is 1. So for 0 houses, we're going to consider it as using 1 toothpick. Now that might not make sense in the technicality of the situation, but we should follow the pattern of the numbers, not necessarily the pattern of the pictures. So numbers-wise, we start with 1 toothpick. So our starting amount is 1. So then our function rule would be the number of toothpicks is 1 plus 5 times the number of houses we want to build. So again, we could use that function rule to find for lots and lots of houses. If we wanted to build 30 houses, we'd have 1 plus 5 times 30. 5 times 30 is 150, and 1 plus 150 is 151. So we would need 151 toothpicks to build 30 houses. Now these rules had our input and output variables. We actually have different names as well for these input and output variables. We can call them dependent, and independent variables. So the independent is our input variable, and it's the variable that you can choose. We can choose how many houses we build. We can choose how many people are going to the movie. Our dependent variable is our output variable, and it's the variable we find. We found that we needed 151 toothpicks to build 30 houses. We found we need $700 to take 70 people to the movie. So input, another name is independent. Output, another name is dependent. These names are more useful for graphing, which is why we have multiple names for these situations. They also relate to the domain and the range. So domain is the x values. It's the input values you could use. So let's take our movie situation. Our domain wouldn't include negative numbers because you can't pick a negative amount of people. You can't have -5 people. So our domain, we could have 0 people, or there's a capacity to the movie theater. There's only so many seats. So let's say there's 200 seats in the movie theater. So our domain for the movie situation would be 0 to 200. Because we can have a minimum of 0 people and a maximum of 200 people, because that's all that would fit in our theater. Our dependent, the values that are possible to use, we call that the range. So output values you could use. That's usually limited by your domain. So again, take our movie situation. We were limited in the number of people we could bring. We couldn't bring negative people. We couldn't bring more than 200. Well, that's going to limit how much we would have to pay. At minimum, we'd pay $0 because no one went to the movies. Maximum, we do 200 times 10. That's $2,000. So it's our possible values that we could use depending on the situation. So let's do one last example. Let's say we have Samantha, who earns $9 per hour tutoring after school. She works no more than 10 hours a week. So let's first identify the independent and the dependent variables. So independent was what we got to choose. So when we're talking about this situation, we have amount we've made, $9, and the number of hours. So how much we're going to make and the number of hours we work. So we can't pick how much we're going to make. We make $9 per hour. That'll add up to a certain amount depending on how many hours we work in a week. So we get to pick, we get to choose how many hours we work in a week. So independent would be the hours worked. The dependent would be the amount we make per hour. So how much we make. Now we can find the domain and the range looking at these. So we said dependent was our range, independent was our domain. So domain, how many hours we're going to work in a week. At minimum, we could work no hours at all. Again, you can't work negative hours, so we can't use negatives. So 0 hours to, well, at maximum, it says we are limited to 10 hours a week. Now, there's nothing in real life necessarily limiting you except yourself. How much do I want to work? So she said, I don't want to work more than 10 hours a week. Or if you have a job, they can limit how many hours you can work in a week. So this was picked by Samantha herself. She said, I only want to work 10 hours a week, no more. So dependent, how much is she going to make? Well, if she works 0 hours, she's not going to make any money, $0. If she works 10 hours at $9 per hour, 9 times 10 is $90. So the range would be 0 to 90. So again, independent was domain, dependent is range. We could also find a function rule for this. So let's say amount made. We're going to say A for amount made. Hours, we'll use H. We use the y equals b plus mx. So y was our output, or our dependent, so amount made is our starting amount. Well, we know our starting amount is $0 if we don't work any hours, so 0 plus the amount of change. You can make $9 every single hour, so 9, and then x, we decided to call it h for the number of hours we worked. And you could simplify that to be just a equals 9h. And then you can figure out for any number of hours how much you are going to make. So that concludes our discussion on patterns and functions.